Hello everyone. Today I want to show you a case study about the member application within IDEA StatiCa. To give you this example, now the general workflow in IDEA StatiCa Member is for the member you're performing a material nonlinear analysis. You're looking at the strains and the stresses. If everything is satisfied, we go on to the linear buckling analysis, where you define or calculate the buckling shape with the corresponding buckling factors. What's more, additionally, you can perform the GMNIA, which is a geometrical and material nonlinear analysis with imperfections. So of the linear buckling analysis, you perform the imperfection on that shape and then adding the load again and then including second order effects, perform the GMNIA. The case study is about the strengthening bracing. The hull is 8.3 meters wide, 22.6 meters long and 2.3 meters high. The critical matter for the analysis is a rectangular or a square hollow section, 50 by 50 by 3 millimeters. It is welded to the other beams IPE 180 on an eccentric gusset plate, and that is an important part. So you see here it is the steel structure, and these are the longitudinal bracings. And because of a horizontal load, wind load in this building, they found out that there is a stability problem in this bracing. And because of the eccentric connections, and it's just a gusset plate, these are sensitive to buckling, to global buckling stability. So the member loses stability and it needs to be strengthened. If we isolate that member, now we see here it's the member modeled in the member application, approximately 3 meters long, with a normal force of 38.72 kilonewtons and the eccentric gusset plate connections on both sides. Now first, before we are going to the more advanced calculations, we do an analytical check manually. So what you see here is a beam hinged, ideal hinge connection, no real stiffness of the connection, and the buckling force is lower than the applied design force, so that means the beam fails due to buckling co-check. Now this is only for the normal actual compression force, but if we also add a bending moment because of the eccentricity in the connections, this unity check will be even higher. So already the analytical check shows us that we have a problem in stability. We are going to model it in the member application, so the longitudinal bracing is modeled together with the connections. So we integrate the real stiffness of the connections, the boundary conditions on both sides, where on the right side we have it's free in the x direction, so it can move in that direction. So it's a simple span, perfect hinged on both sides. Not perfect because we have the stiffness, and we perform the MNA analysis. Now we can evaluate the equivalent stresses and the strains, and you see here the highest stresses in the around the connection. Now if everything is satisfied, so it's below the maximum value, maximum allowable value, we can continue to the linear buckling analysis. You see here there are 6 buckling shapes with the corresponding factors. Buckling shape 1 is the one you see here, so it's the first sinus shape with a factor alpha critical of 1.63, which is really low for global buckling, because that means if we increase or multiply 1.63 with the force that is applied, we will end up in a buckling problem. Now we see also, according to the Eurocode, that for plastic analysis, alpha critical needs to be greater than 15 to be on the safe side. Otherwise, we have to do a more advanced analysis with the imperfections included and the GMNIA. Now here you see buckling mode 2, 3, and 4. So buckling mode 2 is the first sinus, but then in the vertical direction, and 3 and 4 you see the second one, so the full sinus shape. Next, we are going to do the GMNA with imperfections, where the analysis seeks equilibrium in every increment using the initial deformed shape from the LBA's imperfection. Now, if equilibrium cannot be found, the solution stops. Because the member with connections is asymmetric, we need to apply a plus and minus signs to the imperfections, because we have seen like the member is not asymmetric, but because of the connections. You see also that in buckling mode 1, which is in the lateral direction, buckling mode 2 is in the vertical direction, because there you have the connections are stiffer. Now, based on the standards, we choose for buckling curve C and applying a imperfection of around 14 millimeters. And this imperfection we're going to apply on shape 1 and shape 2, and in both directions, so plus and minus, and also the combination of these two to see the greatest utilization. Now you see here, so the imperfection is applied in the shape of that buckling mode. Now, if we perform these analyses, you see here mode 1 in the lateral direction, where already stability issues occur, and in the other direction where everything is fine because the connections are asymmetric, so you have a different results. Then mode 2 is in the vertical direction. You see here both simulations, both analyses are satisfied, and the load can be applied because in this direction there's a high stiffness. And then the last one, the most decisive one, is mode 1 plus mode 2, where we applied in the plus, so plus 14 millimeters in mode 1 and mode 2 directions. So finally you get this shape, and then if we add the loading, so we are adding this normal force here, you will directly see deformations and finally instability problems because the GM and IA does not reach 100% convergence, so the instability of the member is the problem. So what to do? We have to strengthen the member, and the member loses stability and we need to strengthen it. However, since the member cannot be replaced, in this example it needs to be strengthened, and what they did is applying a omega profile to it. But the next question is, how are you going to apply this? Are you going to weld it? It's really difficult and you don't want that, so maybe a different solution. Because what we see, if we don't attach it, if we don't couple these two beams, you see that the sections, they behave independently, so we have to connect them, so the small bolts are added along the length, and we simulate the real exact behavior. Again, we go through the same procedure, so M&A is performed. Now you see here the member with the strengthening profile. Stresses are fine, highest stresses around the connection, and the deformation shows that the members act together because of the bolt connections. After that, we go to the LBA. Now what we see here in the list is the factors. So for shape 1 to 6, factor of 3.57, so the factor was 1.63. That means the buckling factor is increased, so we did a good job. It has a positive result as we expected, but the factor is still quite low and is below 15, our limit value, to say that we can stop here and that it's safe. That means the factor is still below 15. We have to do something else. We have to strengthen it more, or we go to the GM and IA and adding that imperfection again. Important also to mention is that mode 1 and 2 are now switched due to the strengthening. So we saw that mode 1 before it was in the lateral direction, but now mode 1 is in the vertical direction because of that, the shape of that and how that strengthening member is working now. We strengthen it more in the lateral direction. And in shape 2 we have a factor of 6.32, which is increased even more from that 1.63. Well, we have a built-up section now. That means we choose for buckling curve D and having resulting in a higher initial imperfection of around 19 millimeters. We apply that 19 millimeters again to shape 1 and 2, And now we have seen that the most decisive results coming from this combination of minus 19 in shape 1 and 90 millimeters in shape 2. Now we apply the imperfection and go into the GMNIA results. And you see here the results are fine. There is no stability issue. The plates, so the strain in the plates is increased from 0.02 to 0.24, but it's still below 5% and 100% of the load is applied. So that's good. You see the stress results and the deformation results here, which are a bit exaggerated. Now finally, the initial member lost stability due to the normal force, due to the profile and the eccentric connections. Now using the member application of IDEA StatiCa and the GMNIA, so with an imperfection, we proved that the strengthening solution prevents instability, keeps the plastic strain below 5%, and it limits the deflection to an acceptable range. Now, why is this case study so nice to explain to you? Is because we also did a verification study on this example. The verification study is done comparing models of the unstrengthened bracing in IDEA StatiCa Member, the abacus, and the analytical calculation we have seen before. Finally, the comparison showed a 95% match in results, which is quite good. And the objective was to prove that IDEA StatiCa Member is a reliable and validated tool for safe code-compliant design. Now here below you see the member. We have already seen it in the member application, but now we modeled it in abacus in the same way, trying to mimic the same geometry and contacts and bolts and everything. Also using shell elements, as you see here. It looks in 3D, but it's a shell element with a thickness. Performing the same procedure, so the M&A equivalent stress results. Now we see quite similar results here, also for the deflections. So it's around 5 millimeter deflection in both cases. Then the linear buckling analysis. Now the buckling shapes and factors are similar between the IDEA and abacus analysis for modes 1 and 2, the most important ones for us. And here we see for mode 1 alpha critical is 1.64. And in abacus we see an eigenvalue, because that is the same method, alpha critical of 1.57, which are quite similar to each other. We have done the GMNIA, so in the same way, adding a local imperfection of 14 millimeters, because we're working with the unstrengthened member. It's applied and you see exactly or almost the same results. The only difference we see is in the connections, and especially around the bolt holes. In abacus we see some higher stress peaks because of the finer mesh and more integration points around that bolt hole. But overall the results are quite the same, and we see the same results. So that's good, and it helps for our verification process and proof that IDEA StatiCa Member can be used also for you. Finally, I want to show you this slide where the reaction force against the deformation is plotted for the abacus analysis results and IDEA StatiCa Member. One thing you see the difference is that IDEA StatiCa stops where instability occurs. So where there is instability, that you see here also in this graph, it's using a Newton-Raphson model, so it's end of the convergence, and it cannot go on to show you this nonlinear buckling, because it's a linear buckling, and when instability occurs it just stops the calculation. In abacus it is possible to go on, because what you do there is you apply the deformation and you calculate the force. In IDEA StatiCa you apply the force and you calculate the deformation. Now, last thing I want to show you is this is in abacus. So that means after buckling, after instability, you can still perform the analysis and you get nice videos. And that was my last slide. Thank you for watching, and I see you in the next video. Bye bye.